Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at earthquakes and the Earth's interior. So in this video we're going to be focusing on what causes earthquakes along plate boundaries and within plates, and this is going to correspond to section 12.4 of your textbook. So in front of us we have a picture of a divergent plate boundary, in this case an oceanic divergent plate boundary. Now we know that these environments are associated with extensional tectonics, so there's tension, the crust is being stretched. And we can see that in the form of these yellow arrows. We can see that this block of crust here is trying to move off to the left, and this block of crust here is trying to move off to the right. And so of course that means that this area here is under extension, the crust is being stretched out, so it naturally becomes thinner. But of course, because crust behaves as a solid, it's also going to break, so it's going to behave in a brittle fashion, and of course this is going to lead to fault generation. So what processes are occurring along this divergent plate boundary that are going to lead to earthquakes being formed? So we've already touched on the fact that underneath the divergent plate boundary we are going to have the mantle rising up, and it's going to melt through decompression or melting. And of course this is going to produce very large quantities of magma, which is going to start rising through the crust. Now remember, the crust at the divergent plate boundary has been stretched, so it's naturally very thin. So most oceanic crust is typically about 6.5 kilometers thick on average. In contrast, right here at the divergent plate boundary itself, the crust has been stretched out, so it's naturally a little thinner. It's going to be more like 3 or 4 kilometers in thickness probably. So that means entering this area of crust, we're going to have lots and lots of magma, which is being generated down here underneath the oceanic crust. And that magma is going to want to rise. So it's going to move through the crust. And how does it move through the crust? Well, it pushes open joints and faults due to magma pressure, so that the fluid pressure of the magma is great enough that it can actually force its way along joints and along faults and force them open. And obviously this process of pushing the rock apart to make room for the magma is going to lead to the production of quite a lot of earthquake activity. Obviously, we know that at these divergent plate boundaries, the crust is also going to behave in a brittle fashion. It's being stretched, so that means it will eventually fail, it will break, and obviously this will lead to fault formation. Now, we know that in areas which are undergoing extension, the type of fault that we're going to get forming will be a normal fault. And so this is where the hanging wall block will drop down relative to the footwall block. And we can see that quite nicely here. So here is our footwall block, and this block right here represents our hanging wall block, and you can see that it's dropped down relative to the footwall. So this right here is a normal fault. And of course there's going to be fault movement along these fault planes, and of course this is also going to lead to the generation of earthquakes. Now we also have one more source of earthquake activity associated with divergent plate boundaries, and these are the transform faults that connect the segments of the divergent plate boundary. So we can see we have one segment here, one segment here, and one segment here. Now the reason that we have these segments is because different parts of the divergent plate boundary will be producing new oceanic crust at different rates. Some parts will be producing crust quickly, some parts will be producing crust more slowly. And so this means that because different parts of the total divergent plate boundary are moving at different speeds, it begins to break up. Now, in order to allow these pieces of crust to move past each other, you obviously need to have a transform fault right here. So this fault segment, this divergent boundary segment right here is producing new oceanic crust. So it's trying to take this piece of oceanic crust here and push it to the left, and it's trying to take this piece of oceanic crust here and push it to the right. And the same thing is happening here. New oceanic crust is being formed here, so this block's trying to move to the left, this block is trying to move to the right. However, in order to allow that movement, in order to allow this block to go this way and this block to go this way, we obviously must have a fault here. Because if these two blocks of rock were connected to each other, that would obviously make it impossible, wouldn't it? You couldn't have this block going that way and that block going that way if the fault didn't exist. So we need to have a transform fault here to allow these pieces of crust to move past each other. And of course, this is going to lead to earthquake generation because we've got two large pieces of rock moving past each other, lots of friction, lots of energy being built up, and so we're going to get earthquakes forming as a result of fault movement along the transform boundary right here. And very often, this is actually going to be the location where we get the strongest earthquakes occurring along divergent plate boundaries. So the the other types of boundary where we can get earthquake activity occurring is at continent ocean and ocean ocean convergent boundaries. Now, in both of these situations, as we've discussed, we have a piece of oceanic crust which is subducting down into the Earth's mantle. So straight away we know the earthquake activity isn't just going to be focused in the crust, it's also going to be associated with the deeper areas where the oceanic crust is moving down into the mantle. So let's remember that. So at these convergent plate boundaries, so that's ocean ocean and ocean continent, we're going to see a mixture of shallow, intermediate and deep earthquakes. So where are we going to find the vast majority of earthquake activity occurring? Well, we're going to find lots of earthquake activity occurring here along the trench, because of course this is an area where we have a few processes going on. So obviously in this area we have the oceanic crust moving past the continental crust, and so of course once again friction, that's going to produce lots of mechanical energy, which is, and when faults move in that area, we're obviously going to see that in the form of earthquakes. So this area of material here is often referred to as the accretionary prism, and it consists of material which is being scraped off the oceanic crust, which is coming from over here on the left. Now, of course, this process of scraping off material from the top of the oceanic crust, once again, it's not a gentle process. It's something that happens, it's quite forceful. And so this is also going to lead to rocks breaking, pieces of rock being pushed past each other, pieces of rock being deformed, and so once again this is going to lead to lots of earthquake activity taking place within the prism right here. So we have friction along the trench, we have deformation within the prism, and of course we can also see in this diagram we have a few thrust or reverse faults present in the prism as well. Once again, the movement of those faults is also going to lead to earthquake generation. Now, in terms of the actual contact itself between the piece of subducting oceanic crust and the piece of continental crust, this is sometimes referred to as a megathrust. So the reason for this is, if you think of it in terms of a fault, well, imagine this is your hanging wall block here. Sorry, this is your footwall block, I do apologize, and this is your hanging wall block. In a reverse fault or in a thrust fault, the hanging wall block is going over the top of the footwall block. What's happening here? The continental crust is going over the top of the oceanic crust. Therefore, we can, at a very crude level, call it a very, very large thrust fault. And so the contact between the oceanic crust and the continental crust is sometimes referred to as a megathrust. Either way, what we have here is we have two very large pieces of crust trying to move past each other. Once again, that means lots of energy, lots of friction, lots of stress is building up, and therefore we have the capacity for some very large earthquakes forming. Obviously, we have the subducting slab itself, so we've discussed that this is going to be the cause of the intermediate and deep earthquakes, and the reasons being, of course, number one, there's obviously going to be friction between the oceanic crust and the mantle that it's moving through, and so obviously this friction is going to cause earthquake activity as these two large pieces of rock try to move past each other. We obviously have the possibility of the oceanic crust breaking up. Once again, this snapping of the oceanic crust can lead to earthquake activity, and we've also gone and discussed that earthquake activity can also be produced in response to changes in the mineralogy of the subducting oceanic crust. So as the minerals that make up our oceanic crust metamorphose to form new minerals, the change in volume can also lead to rock movement occurring at deeper levels. And so these three reasons help to explain why we see this deep earthquake activity associated with the piece of subducting oceanic crust. Now, the final thing is, obviously, we know at convergent plate boundaries, or should I say ocean continent or ocean-ocean convergent plate boundaries, we obviously have our piece of subducting oceanic crust dewatering, normally somewhere about 150 kilometers down. The water obviously then enters the surrounding mantle, causing it to melt, producing a mafic magma, and that mafic magma then rises up, gets stuck at the base of the continental crust, where it melts the continental crust and will either form felsic or intermediate magma, which then rises through the Earth's crust and eventually in some cases will be erupted in the form of a volcano. So along with the fault movement associated with the tectonic stresses, we also have magma movement. And of course this is going to be in the form of magma simply moving through the crust via dikes and sills, but it's also going to be associated with magma being erupted onto the surface of the Earth via volcanoes. Now, in terms of the mountain range, which is associated with ocean-continent convergent plate boundaries, you can see that we have several large frost faults associated with this mountain range, and this is very, very common. One of the ways that you actually form a mountain range is simply by pushing one layer of rock over the top of another layer of rock and stacking them one on top of another, and this will obviously help you to build up topography, won't it? Because as you stack one layer on top of another you are essentially increasing the height of your crust. And so we can see in this case here, we've got this slab of continental crust here is being pushed over the top of this block, and we have this block trying to move over the top of this block, and this is accommodated through the formation of some very large thrust faults. And once again, just like any fault, these faults will lock up for periods of time, the amount of stress will build up, then that stress will be released as the fault moves, and obviously it will lead to the formation of earthquakes. And these earthquakes here are going to be quite damaging because they'll often be quite large and they're relatively close to the surface, so they'll often be quite powerful. Now, in terms of South America itself, we can look and we can say, and we can analyze the earthquake activity, and it gives us some idea about what's going on. So here's a plan view of South America. So we can see here's the Nazca plate over here, oceanic crust. We have the South American plate over here, which is continental crust. And we can see the trench here, which marks out the position of the subduction zone, where the oceanic crust is subducting underneath the continental crust. So this material along the edge here, just to the right of the trench, this is going to be our accretionary prisms. This is a material that's being scraped off the Nazca plate as it subducts. And then of course we have the Andes mountains here, which represents this area. So this is the area of continental crust which is being deformed in response to the collision between these two very large pieces of crust. Now, obviously, we know this area is going to be full of faults. It's going to be full of fault movement. There's going to be lots of volcanic activity, lots of magma movement taking place. So we know this area is going to be very, very rich in earthquake activity. So we can see that when we look at the diagram itself, we can see all of these yellow, red, and also some green spots, which we can actually see better down here. But we've seen in the previous presentation, just how much earthquake activity there is along this plate boundary. Now, the really great thing that we can do, though, is by using the depths of the earthquake, we can actually see how the oceanic crust is moving down into the mantle. So these earthquakes here, as you can see, form a trend, don't they? You can see there's an arc coming down here. So we have the yellow earthquakes moving into the green ones, moving down into the red ones here. And this represents the position of the piece of subducting oceanic crust. So even though we can't see it very easily, we can use the earthquake activity associated with this piece of subducting oceanic crust to actually show us where it's going. And of course, this is a very helpful and very powerful tool for geologists. It helps us to really understand what's happening with respect to subduction at these convergent plate boundaries. So a classic example would be what we can find out is that we can see the angle of subduction is actually changing. So a piece of oceanic crust is subducting at a relatively shallow level initially, and then as it gets deeper, we can see the angle of subduction is steepening up. And of course, this is going to have repercussions for the piece of oceanic crust, because of course, as the angle changes, it's going to cause the subducting oceanic crust to flex. And of course, this flexing of the oceanic crust can lead to it failing and producing earthquakes. So the final thing we need to think about is how could continental collisions cause earthquakes? So this is the kind of situation we have with the Himalayas, where we have India smashing into Asia. So if we look at this diagram here, you can see we have two pieces of continental crust smashing into each other. So this piece here in the darker grey is going to represent India, and this piece here in the lighter grey is going to represent Asia. So India has been moving northwards and it's smashed into Asia. And so what's happened is the Indian continental crust is actually being underthrust under the Asian continental crust. Now, number one, this means that the thickness of the continental crust is increased because we're stacking two pieces of continental crust on top of each other. Now, obviously, in this environment, we're going to have lots and lots of compressional tectonics taking place. That means both of these pieces of crust are going to be very actively deformed. There's going to be lots of folding happening, but there's also going to be lots of brittle deformation. We're going to have lots of faults forming. And because it's a compressional regime, we know that these faults are going to be either reverse faults or thrust faults. And we can see them here. So here we have a slightly steeper fault. This is going to be a reverse fault. And here we have some slightly shallower angle faults. These are going to be thrust faults. Either way, our faults are going to have this stick-slip behavior. They're going to lock up. Strain is going to build up along the fault plane. Eventually, the stored energy is going to exceed friction. Our fault is going to move, and once again, we're going to have an earthquake. Now, just like the thrust faults associated with the convergent boundary we were looking at a second ago, these faults are going to be relatively close to the surface. If they move in a big way, that's going to produce a large, powerful earthquake which isn't very deep, and so that's going to be very, very damaging. And so you can get some very, very dangerous earthquakes occurring at continent-continent collisions. Now, as we discussed, in terms of the block itself, you can see we have some thrusts here, and of course this represents the plate boundary. There's obviously going to be lots of friction there, so we're going to have some earthquake activity associated with this. But the final thing we need to notice is this piece of oceanic crust right here. Now, this represents the seafloor that was once upon a time in between these two pieces of continental crust. But of course, in order for these two pieces of continental crust to actually hit each other, that seafloor had to be destroyed. So it had to be subducted. And so there is still a piece of oceanic crust which is subducting down into the mantle just off to the side here. And so because this piece of oceanic crust is still subducting, there's still going to be some earthquake generation associated with this piece of crust here. So even though the vast majority of earthquake activity associated with the continent-continent collision is going to be relatively shallow, so it's typically going to occur at depths of less than 70 kilometers, there will be the occasional deeper earthquake, so intermediate or deep, and that's going to be caused by this piece of oceanic crust which is still subducting down. And so you would see these earthquakes have an epicenter somewhere around here on the diagram. Now, in terms of how do we get earthquakes generated within continents? Well, there's a few ways that we can do that. So the first most obvious way we can do it is via transform faults, or faults of any kind in general. The classic example of this would of course be the San Andreas fault, which is in California. So in that case, we have two blocks of rock that are trying to move past each other. Now we know because it's a strike-slip fault, there's going to be no magma generation, so we know there's going to be no earthquake activity related to magma movement, but there is going to be earthquake activity related to fault movement. Now, like most transform faults, it's outcropping at the surface, so you can see the line, the scar of the fault right here. And because this fault is going to be close to the surface, if it moves in a big way, once again, that's going to result in a big, shallow earthquake, which can be very, very damaging. Now, we've also gone and touched on the fact that we can also have continental divergent boundaries, the classic example being the East African Rift Valley. And in this case, we have an area of the crust which is undergoing extension, so it's being stretched. This is going to lead to the formation of normal faults in response to the extension, but it can also lead to decompression melting of the underlying mantle. So we have a situation where we have normal faults being formed and magma being generated, so we have magma movement. And so both of these, once again, are going to lead to earthquake generation. So it's not uncommon to find earthquakes associated with areas which are undergoing active rifting. And once again, the classic example would be the East African Rift Valley. Now, we can also have earthquake activity associated with magma. So the classic example would be a hotspot that gets caught underneath a piece of continental crust, of which probably the best known example would be Yellowstone National Park in the US. In that situation, we have a mantle plume stuck under the continental crust of North America, producing volcanism at the surface, but the movement of the magma through the crust to essentially fill up the magma chambers and eventually feed the volcanoes at the surface will produce earthquake activity. Now, the final way which we can get earthquakes being generated within the continental interior is through the movement of faults which formed due to earlier tectonic processes. So let's just look back at this diagram up here for a second. So you can see that here we have a continent-continent collision. You can see this continent-continent collision has produced lots and lots of faults. Now imagine the collision stops, so the mountain range stops forming, it stops being pushed up, but erosion is going to continue. And if you give it enough time, this mountain range is eventually going to be completely eroded away. And so we would have a ground surface that will just continue straight across like so. All of these mountains here would be gone. However, the faults that were produced by this collision would still be present in the remaining crust. And so it's not uncommon for one of these faults to move. And so you can have a situation where even though the tectonic event that produced the fault could have happened hundreds of millions, maybe even billions of years before, the fault can still move even now, sporadically. And so, it's not uncommon for these faults, which, formed a long, long time ago, to suddenly move. Now, normally that movement will be quite small, so the earthquakes generated won't be that huge. But every once in a while, one of these pre-existing faults can actually move in quite a big way and produce quite a powerful earthquake. We'll actually be discussing the New Madrid earthquake in a future presentation, and that's a classic example of one of these faults formed by a pre-existing event occurring at a later time. All right, thank you for watching, everybody, and have a good day.